Now we enter the construction stage. At this point, students should understand that we are moving from planning and conceptual thinking into building the model step by step. The next slides describe a typical industry workflow from seismic framework to property modeling and uncertainty ranking. This slide summarizes the building blocks. Seismic interpretation provides the major structural input, including horizons and faults. We then build a framework, create a grid, model facies, and finally populate petrophysical properties like porosity and permeability. After that, we calculate volumes and often create multiple realizations, rank them, and select representative cases such as P10, P50, and P90. The key point is that modeling is layered: structure first, grid second, properties third, uncertainty evaluation last. Here you see a typical workflow where seismic interpretation is done first in the time domain, then converted to depth. Thickness maps are created and merged with the structural framework to create a geological framework. In many projects, a test grid is built for quality control before full-scale gridding begins. The key lesson is that the framework defines the surfaces and boundaries that the grid must obey. If the framework is wrong, the property modeling will also be wrong, because properties are assigned to the wrong geometry. This slide introduces the geocellular grid idea in a very intuitive way. The reservoir is divided into many small cells like flexible Lego bricks. Each cell stores properties such as facies, porosity, permeability, and saturation. Grid cell size is a trade-off. Finer grids better capture heterogeneity but require more computing power and more time. Coarser grids are easier to build and run, but they may smear important features like thin barriers, channels, or baffles. Geostatistics is the mathematical framework that allows us to model spatially correlated properties realistically. Unlike standard statistics that may treat points as independent, geostatistics recognizes that reservoir properties vary in space and that nearby values are more similar than distant values. It also recognizes that geological origin matters. Channels have directional continuity, shore faces have layering, and barriers have predictable geometry. In practice, geostatistical methods allow us to create models that honor well data at well locations while generating realistic heterogeneity between wells. Geostatistics is the mathematical framework that allows us to model spatially correlated properties realistically. Unlike standard statistics that may treat points as independent, geostatistics recognizes that reservoir properties vary in space and that nearby values are more similar than distant values. It also recognizes that geological origin matters. Channels have directional continuity, shore faces have layering, and barriers have predictable geometry. In practice, Geostatistical methods allow us to create models that honor well data at well locations while generating realistic heterogeneity between wells. Before property modeling, we must convert high-resolution well data into grid cell scale, a step commonly called blocking or upscaling. A log is measured at centimeter or decimeter resolution, but a grid cell might be 1 meter thick or more. So we need a consistent rule to assign one value per cell. For facies, we often assign the dominant facies in the cell. For porosity, we may use an average. This step is extremely important because it controls how much fine-scale detail is preserved or lost. In conclusion, upscaling is necessary, but it introduces smoothing and uncertainty that must be acknowledged. This slide reminds you that modeling should not start before data analysis. We examine distributions using histograms, study trends with depth or location, use crossplots to see relationships like porosity versus permeability, and analyze spatial correlation using variograms. The purpose is to ensure the model reproduces realistic statistics and geology-based trends. If you skip this step, you may build a model that honors well points but produces unrealistic property distributions overall, which will later produce unreliable volumetrics and simulation forecasts. Facies modeling is where we represent geological architecture, channels, bars, shore faces, floodplains, carbonate facies belts, and so on. The key message is that facies control connectivity. In reservoir engineering, connectivity is everything. It controls whether injected water can sweep oil efficiently, whether faults isolate compartments, and whether wells drain the same connected volume or separate volumes. A good facies model is therefore not only a geological product, it is a flow architecture product. This slide continues the facies modeling theme and typically connects to practical decision-making. If you were planning wells, you would prefer drilling into facies that are expected to have better reservoir quality and stronger connectivity, often clean sands rather than muddy facies. However, good well placement is not only about highest porosity. It also considers proximity to contacts, fault compartments, pressure support strategy, and development objectives. Once facies are modeled, we model continuous petrophysical properties such as porosity and permeability. Here, the key point is the difference between deterministic and stochastic approaches. A deterministic method may create a smooth best estimate surface, but it can underestimate heterogeneity. Stochastic modeling produces multiple equally plausible realizations that honor well data and spatial correlation. This is important because between wells we do not know the truth. We only know probabilities. Stochastic modeling gives us a way to quantify uncertainty rather than hiding it. This slide connects modeling to volumetric uncertainty. Once we have a model, we can compute pore volume and hydrocarbon in place. But because geology between wells is uncertain, volumetrics should be presented as a range, often using P90, P50, and P10. The key message is that volumetrics are not one number, they are a probability distribution. This is how real development decisions are made. Engineers and managers ask, what is the conservative case, the most likely case, and the optimistic case? Ranking realizations helps select representative cases for further study and simulation. This slide shows petrol as an example of a widely used industry platform for reservoir modeling. The key message for you is not to memorize software brands, but to recognize that industry workflows are executed in integrated platforms where seismic interpretation, well data, gridding, facies modeling, and property modeling are linked. Understanding the workflow conceptually will allow you to adapt to any software environment later, whether commercial or open source. This slide highlights another major modeling ecosystem. Again, the key point is that multiple platforms exist, and companies choose tools based on licensing, integration, and specialty features. Your engineering value as a professional comes from understanding the modeling logic and quality control. Software is the implementation tool, not the true expertise. This slide is very exciting for modern students because it shows that structural modeling can also be done in open-source Python frameworks such as GemPy. This supports reproducible research workflows, integration with machine learning, and customizable modeling pipelines. Here, I want to emphasize that open-source tools allow students to learn the principles of implicit structural modeling without being limited by commercial software access. It also shows how petroleum engineering increasingly intersects with data science and computational modeling. This slide introduces machine learning as an emerging tool in reservoir modeling. Machine learning can assist in tasks such as facies classification, property prediction, automated interpretation, and fast uncertainty exploration. However, the most important point is that machine learning is powerful when it accelerates workflows and learns patterns from data, but it must be constrained by geological understanding and physical realism. The best modern workflow is often hybrid, geological concept plus geostatistics plus machine learning support where appropriate. Now we connect reservoir modeling to carbon capture and storage. For CCS, we also need a detailed subsurface model because storage safety depends on structure, seal integrity, injectivity, pressure buildup, and plume migration pathways. A carbon storage reservoir model must characterize not only the reservoir but also the caprock, faults, and boundary conditions that control pressure dissipation. This is an important career message. The same modeling skills used for oil and gas are directly transferable to CO2 storage, with additional emphasis on containment risk and monitoring design. This slide shows an example reservoir model and permeability distribution for simulation purposes in Poland. What modeling for CCS means in practice: you build the reservoir framework, model permeability heterogeneity, and then run simulations to test injection scenarios, plume spread, and pressure evolution. Permeability distribution is crucial because it controls injectivity and pressure propagation. If permeability is low, pressure rises quickly and risk increases. If permeability is high, plume migration may be larger and monitoring must cover a wider area. So CCS modeling is fundamentally a trade-off between injectivity, capacity, and containment. This slide brings the story closer to Japan. Japan's pathway to carbon neutrality will likely require large-scale CCS solutions, and those solutions require high-quality subsurface modeling. The modeling process is the same in principle: structural framework, gridding, properties, uncertainty, but the evaluation focus shifts toward long-term security, integrity, and monitoring. This slide is a great place to motivate students. Reservoir modeling is not only about producing hydrocarbons, it is a major tool for subsurface climate solutions.